Hi everyone, my name is Anirban Goggopadhyay and today I am excited to present my master thesis titled Fact Check, an agent-based retrieval-augmented framework for fake news detection and explainable verification. So this work was completed at Liverpool John Moores University under the guidance of Dr. Monica Reddy with additional support from faculty at Upgrad and LGMU. So the motivation behind this work comes from the growing challenge of misinformation online and the rising need for systems that are not only accurate but also transparent. Over the next few minutes, I'll walk through the motivation, architecture, experimental design, results, and practical significance of this project. With that, let me move to the next slide. So this slide describes today's agenda. I'll start with the background, why misinformation is such a critical global issue today. Then I'll summarize the literature review and highlight the major limitations in current approaches. So this leads into our aim, objectives, and key research questions. Next, I'll explain the methodology, dataset, and the system architecture, followed by the experiments and evaluation metrics used. We'll then go through the results and discuss what they imply. Finally, I'll conclude with the main contributions and recommendations for future work. So here we'll cover the background briefly, why fake news detection matters. Misinformation continues to rise because of how drastically social media has reshaped news production and consumption. Platforms offer instant publishing. Anyone can post anything, and the speed and reach of content often amplify false stories. Engagement-driven algorithms reward sensational or emotional posts, which increases visibility of misleading narratives. Also, low media literacy in many demographics contributes to the spread. Because false information travels much faster than corrections, users often see and react to misleading content before any verification arrives. So this makes robust, evidence-based, and scalable detection systems absolutely essential in today's digital ecosystem. With that, let me move to the next slide. So here we'll cover the literature review briefly. So how the fake news detection has progressed through three main eras. We'll start with the early machine learning methods. These methods used lexical features like n-grams, DF, IDF, and sentiment markers. Now, these models were lightweight and achieved good baseline accuracy on small datasets, but they only captured surface level signals and they struggled with new topics. So then came the deep learning era that introduced CNNs, RNNs, and bi-LSTMs. So these models captured semantic relationships better and improved generalization, but they still acted like black boxes with limited interpretability. Then happened the transformer revolution. It brought models like BERT and DistilBERT that delivered strong contextual reasoning and excellent benchmark accuracy across datasets. However, even these powerful models typically behave as level-only classifiers and they do not provide evidence or explanations. This is the major gap my project aims to address. So let me move to the next slide. So despite advancements, here we'll just cover the problem statement and the research gap. Now, despite advancements, several key problems remain unresolved. Most fake news detection systems are closed-world classifiers. They look only at the input text and output a label like real or fake, but without any supporting evidence. Now, users don't know why something is flagged as fake, reducing trust and usability. Systems also struggle with cross-topic generalization because they are not connected to real-world factual sources. Finally, very few studies integrate external evidence sources such as Wikipedia or fact-checking APIs directly into the pipeline. Now, my proposed direction is to build a retrieval-augmented agent-based systems that links claims to external sources, verifies them using transformers, and generates a human-readable explanation. So with that, let me move to the next slide. So this covers the aim and objectives of this work. Now, the aim of my research is to design and evaluate a unified framework that combines retrieval, verification, and explanation into a single agent-based architecture. To achieve this, I set six key objectives. So first, review prior work. We should review prior work across linguistic, deep learning, transformer, graph, and multimodal approaches. Second, build a retrieval agent that blends BM25 and mini-LM embeddings for richer evidence retrieval. Third, fine-tune Distilbert to act as an efficient verifier agent. And then fourth, develop an explainer agent capable of generating natural language justifications grounded in retrieved evidence. And fifth, benchmark several models, baseline, transformer only, hybrid, and hybrid with external evidence using standard metrics like accuracy, precision, recall, F1, and AUROC. And finally, assess explanation quality by using a small human evaluation study focusing on clarity and faithfulness of the explanation. So let's move to the next slide. So this covers the research questions and hypotheses. So my work revolves around three core research questions. The first asks how a multi-agent pipeline performs compared to traditional single model baselines. The second examines whether integrating external evidence such as Wikipedia or Google Fact Check improves accuracy and user trust. The third evaluates whether explanations generated by the system are clear, reliable, and evidence grounded. I formulated four hypotheses corresponding to these questions. In summary, the hypotheses state that external evidence improves verification performance, explanations enhance interpretability without harming accuracy, multi-agent architectures perform more robustly across topics, and hybrid retrieval produces higher evidence coverage than individual methods alone. So with that, let me move to the next slide. Here we will go over the scope, assumptions and significance of this project. The scope of the project is clearly defined. It focuses exclusively on text-based misinformation using the well-fed dataset. The system uses three agents: retriever, verifier, and explainer, orchestrated through LangChain and LangTurtle. There are no multimedia signals, no social network metadata, and no training of transformers from scratch, only fine-tuning. Several assumptions underpin the design, such as the reliability of external knowledge sources and the feasibility of hybrid retrieval returning at least one relevant passage. The academic significance lies in unifying retrieval, verification, and explanation into a single model pipeline. The practical significance is equally important. This approach supports journalists, fact checkers, and automated systems with transparent evidence citing outputs suitable for real world deployment. Let me move to the next slide. So here we'll go over a brief overview of the dataset. The dataset used is WellFleck, which contains over 72,000 English news articles. Each instance consists of a title and body, and I combine them to form a consolidated claim text. The dataset is balanced across real and fake levels, about 35,000 real and 37,000 fake articles, which helps reduce bias. And WellFake is language clean and free from images or social signals, making it ideal for experimenting with retrieval-augmented text models. The dataset coverage summarizes the key attributes, and the claim formation diagram shows how text samples were structured before feeding into the pipeline. Let me move to the next slide. So here we'll go over the overview of the research methodology. Now, my methodology consists of 5 sequential stages. Stage 1 is dataset preparation, including text cleaning, normalization, and deterministic splitting into train, validation, and test sets. Stage 2 is the core pipeline, retrieval, verification, and explanation. Each claim goes through these 3 stages in sequence. Stage 3 covers model implementation, including training TF-IDF and logistic regression as a baseline, and fine-tuning Distilbert as the primary transformer verifier. Stage 4 integrates external evidence sources like Wikipedia and Google Fact Check, Google Custom Search Engine, etc., which act as additional supporting information. Finally, stage 5 involves evaluation using standard classification metrics, retrieval metrics like coverage and MRR, and a small human evaluation study to assess clarity and faithfulness of explanations. This structured methodology ensures a complete end-to-end evaluation of the fact check framework. Let me move to the next slide. Here we'll cover system architecture and design. Now let me walk you through the system architecture. That entire pipeline is implemented on an NVIDIA L4 GPU running on Ubuntu 22.04 using Python 3.10 and PyTorch 2.2. The architecture has three major components: the retriever, the verifier, and the explainer. The retriever combines both lexical BM25 search and mini-LM semantic embeddings. These rankings are merged using reciprocal rank fusion, which ensures neither lexical nor semantic signals dominate. The retriever outputs the top k most relevant passages from the well-fed corpus and, when needed, external sources. Next, the verifier uses multiple models, a TF-IDF plus and logistic regression baseline, a distal BERT transformer, and finally, a hybrid verifier that fuses their signals. The hybrid logic helps avoid lexical bias, also stabilizes uncertain cases, and produces more consistent factual decisions. And finally, we have the explainer. This module generates short, concise, and fully extractive justifications. It assembles actual evidence centers and performs checks for grounding, citation, alignment, and coherence. All of these components are orchestrated using LangChain and LangGraph with FICE GPU and Hugging Face transformers powering the retrieval and model layers. Let me move to the next slide. So this slide explains the local retriever in detail. The lexical module uses BM25, which is fast and ideal whenever exact words or named entities appear in the claim. The dense module uses mini-LM embeddings with FICE GPU to capture paraphrasing and semantic similarity. This helps when the wording in claims differ from the evidence. And both outputs are merged using reciprocal rank fusion, giving us a stable hybrid retrieval across different claim types. The system retrieves all evidence directly from the well-fed corpus, the title and body text of all 72,000 articles. This ensures contextual consistency. In terms of efficiency, BM25 is extremely fast, and FICE GPU enables sub-second embedding searches. End-to-end retrieval here takes about 1 to 2 seconds, including ranking and fusion. On the right, you can see two curves, coverage versus K, showing that around K equal to 6 to 8, the coverage almost saturates. And top K saturation again confirming that relevant evidence usually appears in the top ranks. So here is the next slide. The next part of the retriever extends beyond the dataset. For claims that require world knowledge, entity background, or authoritative information, we query three sources: Wikipedia, Google Fact Check API, and Google Custom Search Engine. Once retrieved, all pages go through a dedicated evidence processing pipeline that comprises of text extraction, BM25 and mini-LM scoring, a semantic threshold to remove noise, and finally selection of only high-quality supporting passages. This external retrieval achieves around 0.89 coverage, especially helpful for entity-heavy or real-world claims. The system does not always call external sources, only when the internal retriever is insufficient. So this avoids unnecessary latency while still expanding factual grounding. Let me move to the next slide. Here you can see how the three verification models behave. The baseline TF-IDF and logistic LR combined classifier is fast and interpretable, but struggles whenever the claim wording changes or contains paraphrasing. The distal BERT transformer learns contextual meaning and performs much better on long-range semantics. And after fine-tuning for 30 epochs, it reaches an F1 of about 0.976. Finally, the hybrid verifier combines the strengths of both lexical precision and semantic understanding. It consistently resolves borderline cases and gives the best performance. Accuracy is around 0.980 and F1 is about 0.979 with the hybrid verifier. So the bars just show this progression as we move from baseline to transformer to hybrid. Both accuracy and stability increase. Let me move to the next slide. So this slide focuses on how explanations are generated. Our system produces purely extractive explanations. That means it only selects and arranges sentences from retrieved evidence. There is no paraphrasing or hallucination. We also add inline citation markers like 1 and 2 in square brackets that point directly back to the retrieved passages. The explanation pipeline has 4 steps. First, snippet selection using BM25 and mini-LM and MMR to pick the diverse high signal sentences, and extractive assembly to combine them in a logical order, then a citation binding to ensure every sentence traces back to evidence, then post-processing checks for grounding and readability. The final output is short, coherent, and fully grounded in real evidence. Let me move to the next slide. So here we'll cover explanation evaluation. To evaluate explanations, we use human-centered metrics. The first metric is faithfulness. It does the explanation. So this answers the question like, does the explanation strictly use retrieved evidence without adding unsupported statements? The second metric is clarity. Uh, the, it answers the question of, is the explanation easy to follow and contextually meaningful? We also evaluated the system across claim types. It performs strongly for policy, factual, and event-based claims. It is less stable for emotionally charged rumors or claims with limited lexical cues. On the right, I have included an example of a claim and its extractive explanation along with citations. And below that, you can see the comparison between faithfulness and clarity across different topics. Let me move to the next slide. Here is a slide walkthrough of how a claim travels through the system. User gives a claim. The hybrid local retriever first searches the welfare corpus using BM25 and mini-LM with RRF Fusion. Then the internal hybrid verifier examines the claim evidence pair using TF-IDF and logistic regression and Distilbert. If required, the system also pulls external evidence from Wikipedia, Google Fact Check, or custom search engine. And finally, both internal and external verification signals are combined to produce the final verdict, real or fake. An agreement between verifiers strengthens this decision, and contradictions directly flag potential misinformations. This slide shows the explanation workflow in detail. The explainer selects high-value sentences from retrieved passages using BM25 and mini-LM scores. MMR is applied to remove redundancy. Next, snippets are ranked based on semantic relevance and lexical support. The system then assembles the explanation by copying sentences verbatim. Again, no generation and no rewriting. Citations are attached to each sentence, guaranteeing full traceability. Finally, grounding checks ensure that every sentence in the explanation exists in the retrieved evidence. This ensures zero hallucination and maximum trustworthiness. Here we'll focus on results and discussions. So these are the key results of the system. Retrieval performance reaches a coverage of 0.99 at k equal to 10 with high MRR. Important evidence is usually retrieved early. Verified models show strong results with the hybrid verifier achieving around 0.982 accuracy and 0.980 F1. The external evidence verifier achieves around 0.987 accuracy and helps resolve cases where welfare alone is insufficient. For explanation quality, faithfulness is extremely high because everything is extractive and clarity is strong for factual domains. In the insights section, you can see how BM25 and mini-LM complement each other, how external evidence boosts factual grounding, and how hybrid verdicts reduce both lexical bias and semantic overgeneralization. So let me move to the next slide, that is limitations, that covers the limitations of this project. So first of all, the welfare dataset itself contains synthetic or republished articles and lacks multimedia social metadata. This means it may not fully generalize to real breaking news environments. The external retriever depends on the completeness of Wikipedia and Google Fact Check, which may miss niche or emerging claims. Model-wise, fine-tuning Distilbert was limited by available compute. We also did not experiment with larger LLM verifiers or cross-encoders. Explanations are purely extractive. They do not perform deeper reasoning. And finally, human evaluation was pilot scale with no annotated agreement due to limited reviewers. Despite these constraints, the system demonstrates strong retrieval, verification, and explanation performance while maintaining complete faithfulness. Let me move to the uh, next slide that summarize the key learnings from this project. First of all, retrieval augmented verification works. Combining BM25 with dense retrieval and distilled verification clearly outforms text-only baselines. Hybrid retrieval consistently brings relevant evidence to the top, improving both accuracy and robustness. Secondly, hybrid verifier means complementary strengths. Lexical and transformer models compensate for each other's weaknesses. The hybrid setup reduces overgeneralization and handles paraphrasing and long sentence reasoning more effectively than either model alone. External evidence helps in real-world scenarios as well. Adding Wikipedia, Google Fact Check, and custom search engine strengthens verification, especially when the dataset lacks context. This shows that grounding claims in real-world knowledge is essential for trustworthy fact-checking. Next, we also see that explanations improve transparency. For factual claims, explanations were faithful and clear. For emotional or rumor-heavy claims, evidence can be noisy, highlighting a natural limitation in current models. So finally, let's get to the overall conclusion. So basically, a modular retrieval augmented architecture is a strong direction for practical fact checking. At the same time, improving explanation reliability and domain generalization remains an important future challenge. Let me move to the next slide. This work contributes to knowledge on several fronts. Methodologically, it operationalizes a hybrid retrieval strategy using BM25 and Mini-LM with reciprocal rank fusion and presents a systematic comparison of baseline transformer-only hybrid and hybrid plus external verification models. This gives a more complete picture of how retrieval and verification should be combined for factual consistency. Architecturally, the work proposes a clean, modular pipeline, retriever to verifier to explainer, coordinated through LangGraph. This design not only supports controlled experimentation, but also lays the foundation for future multi-agent extensions. In terms of interpretability, the project introduces a lightweight but effective framework for evaluating explanation faithfulness and clarity. It also highlights how explanation stability varies across domains, especially between factual claims and more emotionally charged or ambiguous content. Finally, conceptually, the project reframes OLPEC as more than just a classification dataset. It positions it within an evidence-augmented fact-checking setting, showing how retrieval behavior, model performance, and explanation quality interact as parts of a unified system. So let me move to the future recommendation slide. So looking ahead, this work points to several promising directions. The first is to move towards a full multi-agent fact-checking framework. Specialized agents could handle tasks such as evidence ranking, contradiction resolution, claim tracking, or domain adaptation, gradually evolving the system into an open domain verification ecosystem. The next direction involves more rigorous robustness evaluation, testing the system on adversarial examples, cross-domain claims, and domain shift scenarios, especially in areas like health or crisis misinformation, would reveal how well the model generalizes beyond its training landscape. Another important direction is improving human-centered explanation design. Larger human evaluation studies, structured argumentation, and better citation clarity would make explanations more trustworthy and intuitive for real users. There is also room to enhance evidence reliability by incorporating metadata such as credibility scores, fact-checker confidence, or source provenance. This would ensure that the system evaluates not only relevance but also trustworthiness. And finally, extending the pipeline to multimodal verification, incorporating images, videos, and social media signals would help the system keep pace with modern misinformation formats. Together, these recommendations outline a path toward more reliable, more transparent, and more generalizable fact-checking systems. So that is the end of this presentation. Thank you for watching this demonstration. I hope the walkthrough provided a clear understanding of the system and the key contributions of this work. Thank you.